Okay, so when this curve is used to represent my probability, then we call this curve a probability density function. Okay, and the curve has a function, right? And this function, I'm going to call it f of x. So, okay, and this curve, this function, in fact, f of x, okay, is called a probability density function. And this is a very powerful function. Why? Because it allows me now to use areas to find a probability. So only by looking at area under the curve, I will find the probability of a range of this variable. So, for example, here I'm illustrating a PDF, a probability density function of the variable that can go between A and B. So that's why you can see that the area under the curve is equal to 1, because if I know that x can take only values between A and B, so that's it. The cumulative probability of having the variable within this range should be equal to 1. That's it. It cannot take any other values. That's why the area under the PDF, the probability density function, is always equal to 1, which reminds us of remember the property of a discrete probability distribution that says sum of p of x is equal to 1. Remember that we use this a lot, right? And this is the same in here. But now, because it's not discrete, it's continuous, we look at area, okay? And the area will be equal to 1 because it represents the probability. And what we're going to learn later is that it's not necessarily that we're looking only at the whole curve, of course, because this is easy. It's always equal to 1. But what if I'm interested to see what the probability that x, I'm sorry about that, I'm using my mouse to show these. What about the probability that x is within this range? All what I do is to find the area under the curve that's shown here in this hashed area. And how do we do it? It's easy. Once you have f of x, then you can find the area. Okay, let's proceed. So keep in mind that whenever you're looking at a probability density function, PDF, I'm going to always refer to it as PDF, okay? We have two requirements, very similar to the requirements that we had for a discrete probability. Okay, what are these two? First of all, f of x should be always greater than 0, okay? So we're looking at the curve which is on the positive side of the vertical axis, and then the total area under the curve between A and B, where if we are given that this variable can take any value between A and B, so this will be given to us, then the area under the curve under f of x will be equal to 1. This is very important. Okay, and this will let you know whether you have really found the right f of x, okay, or if it's missing anything. Okay, so we're going to see that a lot. We're always going to verify whether these two requirements are met. So let's start with a very simple distribution, the uniform distribution. What's a uniform distribution? By the way, we have a variable can have a discrete uniform distribution or a continuous uniform distribution. What do we let me explain first the discrete, because it will allow you then to better understand the illustration that I'm going to show you, and also understand better what's a uniform distribution. If we have a variable x that has a discrete probability distribution, and it can take 3 values, for example, or let's say 4 values, 4, 5, 6, 7, okay, 4, 5, 6, 7, and this variable will have a uniform discrete distribution if the probability of each value is the same for all the others, So in this case, because there are 4, the probability of each one is 0.25, right? If they are 5, then the probability of each one is 0.2. They have exactly the same probability. Now, a variable also can have a continuous uniform distribution. So this variable x, for example, has or we know that it has a continuous uniform distribution, and x can be between the two values, the lower limit a and the upper limit b. I know that it's always there. And how do I represent then its probability density function? Remember, probability density function, it's a function below which the area represents the probability of occurrence of this variable, and we know that the whole area will be equal to 1, and I'm going to use this property in order to figure out what's the shape of my probability density function when it is uniform distribution. Okay, tell me now, what's the probability that x is between a and b? Of course, these are all the occurrences, so this is equal to 1, right? Now, because it is uniform, that means the probability density function will be horizontal, right? Like that, because the probability of every value is exactly the same. So the probability of a range within the probability within any range will be equal to the probability in a similar range, and that's why this is represented by the horizontal line. But the big question is, what's the height of that? Okay, what's the height of this one? Meaning that what would be then this value here? I know it's horizontal line, but what is the value of that horizontal line? The answer to that is very easy. Remember, we are looking for an area under the curve is equal to 1. So all that area should be equal to 1 because it represents the whole probability. And this area, okay, what the geometric shape of this area is a rectangle, and the area of a rectangle is equal to the base times the height. The base is equal to what? Equal to that distance, which is what? Which is equal to b minus a, right? It gives me that distance now. So the base is b minus a. I need to multiply it by something to make the area is equal to 1. So I need to multiply it then by the inverse of that, by 1 over b minus a, right? Now when I multiply the base, okay, the base b minus a times the height, which is now 1 over b minus a, I get 1, which is the area, which makes that f of x is my probability density function. Okay, and that's why a uniform distribution has this value always, or this function, 1 over b minus a, where b is the upper limit and a is the lower limit. And now I'm able to find the probability of any interval for x. Okay, for example, if I'm interested of, let me first clean this up so that it does not confuse you, because I'm going to show you another area now coming. If I'm interested to see what's the probability of x within the interval x1 and x2. Okay, so this is x1, this is x2. Let me take out these. Okay, and so what do you think is this? Again, we're talking about an area, so it will be finding this area. And what's that area? It's a rectangle, so it's equal to the height, 1 over b minus a, times the base, okay, which is what? Which is x2, again, x2 minus x1. It will give me the base, and here we go. This is how we find it. Very easy. So here is an example to illustrate the use of probability density function when the variable has uniform distribution to find the probability of x being within any range. Okay, so we're given that we're given that the amount of gasoline sold daily at a service station is uniformly distributed with a minimum of 2,000 and a maximum of 5,000. And we have different questions about different ranges of that variable. So first, let's draw the curve for the probability density function. So I'm going to refer to X as being the amount of gasoline sold daily. Okay, it's very important that we define the variable. So this is our X, and we know that X, and usually we get this from historical data, is between 2000 and 5000. So we learned from previous slides that the PDF of a uniform distribution will be a horizontal line, and the height of this horizontal line, meaning that where it touches the vertical axis, will be equal to what? 1 over b minus a, where b is the upper limit, a is the lower limit. So in this case, it's equal to 1 over 5,000 minus 2,000. So that's equal to 1 over 3,000. Once we have that, then we are ready to find the probability for any range. Why? Because we know that the probability represents the area under the curve. Just a quick reminder here, what do we mean by representing the PDF as being a horizontal line? Remember, what's the function of a horizontal line? It's f of x equals c, right? It's a constant because it does not change. That's why it's on a horizontal line. So in this case, as f of x is equal to 1 over 3000, all right? This is our the function itself. So to answer the questions, A, find the probability that daily sales will fall between 2,500 and 3,000. So let's show these on the graph, 2,500 and 3,000. So we learned that probability equal to the area under the PDF. So here we go. This is the area. And the question, what's this area A1? It's a rectangle, so that's very easy. It's equal to base times height. Okay, so it's b times h1, height. Sorry, in fact, I should have written here h times b1 because h is not changing. I'm very sorry about that. And b will be changing within, depending on the range. Height is always equal to 1 over 3000. So it doesn't matter, it's height times base. So that's equal to 1 over 3000, the height, times 500. Why 500? Because this is the difference between 3000 and 2500, right? So it's 0.167. Very easy. Part B, what's the probability that they will sell at least 4,000? What does it mean, at least 4,000? That means 4,000 and above. And we know that there's an upper limit of 5,000, in fact. Don't forget that. So on the graph, here we go. It's this area that I'm going to denote as A2. And then, which means that probability that X is greater or equal than 4,000 is equal to A2, which is again equal to, it's equal to the height times the base. And again here, forgive me about that, it's the height times b2. It's not h2 because h2 is not changing. Okay, so let's take this out, and it's times b2. So that's equal to what? The h is 1 over 3000, and what do you think about the base? Yes, it's 1000, right? Because it's the difference between 5000 and 4000. So we get 0.333. Part C, what's the probability that they will sell exactly 2500? What do you think? I want you to really think about it before I, or just pause the video and try to think about it. Hopefully that you thought about this. And we know that when the variable is continuous, the probability of a specific value is equal to 0 because it's that small that you can easily approximate it as being equal to 0. Okay, so I hope that this example reinforced what you had just learned about the probability density function and a uniform distribution.